All right, finally. All right, so let's just start a little bit with the history of like processor manufacturing. So let me start with asking a question. So what is the Moore's law? Anybody knows?
Was it the doubling of transistors?
Yes, that's true. So, and thank you. So based on the Moore's law, which is a kind of prediction rather than a law, we know that the number of transistors are doubling every 18 to 24 months, right? And then you can see this kind of linear trend in the increase of the number of transistors, okay? But when we take a look at the process frequency or the clock rate, we see that we are basically kind of flattened after, let's say, 2005, right? Why do you think this happens? Although that we are increasing the number of transistors, we got a linear speed up to some point, like here, right? But after this point, the linear speed up is over. Why do you think that's the case? Any ideas?
The technology had some physical limitations that cannot be overcome that easily.
Yes, but what is that physical limitation?
Precisely, I do not know.
Okay, so any other ideas?
Maybe because if you want to include a lot of transistors in a fixed, say, area, you can't get to the transistors to be, there is limitation to how small the transistor can be.
Well, okay, that's also is one of the reasons, but not the main reason. So the main reason,
Maybe high temperature?
yes, that's true. Yes, exactly. So when you want to have more clock frequency, you basically want to have more power, right? So more power is needed for more frequency. And when you have more power, it means you are generating more heat. And then if you generate like heat, like without any control, then what happens? It melts down the CPU, right? Or the chip. So because of that, we reached a kind of power wall here where you couldn't really increase the power of the chip because of the heat, right? So back in the time, because of this limitation, they started to implement some advanced hardware implementation techniques to still kind of make this trend better that you can see in this orange trend, right? So it's still not linear speed up, but a little bit better. And like these optimization techniques also reach the limitation. So you really cannot reach this linear trend, right? So what is important to know here is that before 2005, if you had a program that you, I don't know, wrote in 2000, and if you run that program in 2002, you could see that your program, like the performance of your program was roughly doubled. But that stopped after 2025. So in 2005. So after 2005, if you had a program written some years ago, and then if you run it on a newer CPU models, still you don't get any performance, right? All right. So how the hardware companies they respond to this was to use this transistor rather than. So this was the main idea and the most important idea that we still use today. So instead of using that amount of transistors that we are still doubling all the time for increasing the clock frequency, why not using them and build more cores, right? Rather than just increasing the speed of one core. So starting from 2005, people started to develop multi-core systems, multi-core platforms, right? And you can see after that, the number of cores are increasing, right? So what is the challenge when it comes to multi-core programming, well, to multi-core systems? The programs are not aware of these like multi-core architecture by default. So it's up to the programmers and developers to optimize their code for these multi-platforms, multi-core systems, and to make them aware of that architecture, right? So that's why after 2005, it was so essential that you could write parallel programs that could use these multi-core benefits, right? Otherwise, you basically cannot improve the performance. And that's because of this parallelism power that we have, that now we can train large-scale AI models. Otherwise, although we had the knowledge and the algorithms were there before this time, but that's because of the parallelism and like high performance hardware that we can really train these kind of models. All right. So that's kind of important to know how to write parallel programs and how to use these multi-core machines and now multi-node machines. Like you should be able to write a program to run on hundreds of thousands of GPUs, and all of them, they have the multi-core systems. I mean, that's a massive amount of parallelism that you should exploit by your programs. All right. So any questions about this? Okay. So then after this became a trend, so people started to think about different kind of design approaches for computing systems, right? So the first approach is called latency-oriented design, and the other one is called throughput-oriented design. So can anyone explain to me what is the latency-oriented design and what is the throughput-oriented design? Any guess?
Throughput is related to the processing power, or
No, it's about the design of the like hardware design, but it can be also applied to other things. So latency-oriented design is like to have a very fast car. So what's the goal here? The goal here is to minimize the time that it takes to perform a single task, right? Or a very few number of tasks. So this is usually done when you want to like do something very fast without the latency, right? But on the other hand, the throughput-oriented design, the goal of throughput-oriented design is to maximize the number of tasks, right, that can be performed in a given time frame. So that's the main definition of the throughput. You want to do more per time, but here you want to do something very fast, right? Okay, so can anyone make an example of a latency like critical application? So what kind of application you can have in mind in which the latency is super important, so you don't really want to have delays?
Maybe gaming.
Yes, that's true. Yes. So in gaming, you don't really want to have delays, right? So that's why people always nagging when it comes to online gaming. So because of there's some like high ping. Okay, what about the throughput-oriented applications? Any ideas?
Batch processing.
Yes, that's true. Any other suggestions?
Well, the training of different AI models.
Yeah, that's true also. Yes. All right. So when it comes to throughput-oriented design, like for example, training an AI model, You want to process as much as data as you can per time. But in the same AI like field, you want to serve the model as fast as possible. So you want to reduce the latency of the model serving. So for example, when you use ChatGPT, you want to get the answer as fast as possible. But when you are training something like ChatGPT, you want to process as much as text as possible, right? So this latency oriented and throughput like oriented comes from the application needs. So the hardware needs to provide support for that, right? So now let's talk about the hardware a little bit. What kind of between like what is the CPU built for? Is CPU designed for reducing the latency, or was it designed to maximize the throughput? If you think about the CPU.
Throughput, I guess.
What?
Throughput.
Okay, any other suggestions? You can think about cache memory. Why do you use big caches when it comes to CPU? What's the main goal?
To minimize the time
Faster.
What?
of the fetch.
To make things faster.
Yes. Okay. Sorry, I didn't hear you. Can you repeat, please? Online?
To minimize the amount of time taken for the fetch.
Yes, that's true. So now when you think about it, is CPU latency oriented, like a processor, or a throughput oriented processor?
Latency.
Yes, it's latency oriented because they're doing a lot of sophisticated and like complicated techniques just to make the instructions execute on CPU faster, right? And on a multi-core CPU, you probably have like, I don't know, 16 cores, 24 cores. So you still cannot do like huge amount of things at the same time. Okay. All right, so CPU has a latency oriented design, right? And on the other hand, GPUs, they have throughput oriented design. So that's one of the main differences between CPUs and GPUs when it comes to hardware design. So let's compare them side by side. So in this figure, assume that the area of each block is the area really occupied on the hardware. So when it comes to CPUs, you see that we have a very big cache, you have a very big control unit, and you have like big, powerful, but a small number of ALUs, right? But when you see the GPU architecture, you see that you have much smaller cache, right? A smaller control, so you don't have a sophisticated control mechanism, but you have so many ALUs. So if you think about it, you see that you can do a lot of things at the same time because you have a lot of ALUs, but each task individually might not be faster than the CPU execution, because in CPUs you have a sophisticated control and large cache, right? So therefore, in CPUs you have a few but powerful ALUs that are designed for reducing latency, but in GPUs you have many but small ALUs, right? The latency is not low, but the throughput is very high, right? So as I mentioned, for CPUs, you have large caches, right? So because you don't want really to stall for accessing data in the memory, but in GPUs you have a small caches. And if you see in the diagram and you think about the hardware area, you see that most of the area in a GPU chip is dedicated for computing, right? But here, most of the area is dedicated for reducing the latency, right? Okay. So CPUs, they have sophisticated control. So if you took like advanced computer architecture courses, you are familiar with branch prediction, data forwarding, and some other techniques. And however, in the GPUs, you don't have sophisticated control, right? Okay. And then when it comes to CPUs, you have modest multi-threading to hide short latency. So for example, in the CPUs to hide stalls and latency, so you have multiple hardware threads on your device, on your system. Then when a stall happens, you just switch to another thread, right? So because you don't have a lot of threads per core when it comes to GPUs, so you have modest latency hiding. But when it comes to GPUs, you have a massive number of threads. Then you can hide the latency much better, right? So GPUs are better in hiding the latency. Hiding the latency is not necessarily the same as reducing the latency, right? Because you're just hiding that. Okay. And CPUs usually have a high clock frequency and GPUs usually have a moderate clock frequency. Okay, so you can really see that GPUs are designed for maximizing throughput and CPUs are designed for minimizing the latency. A smart application should use both of them. So if you want your application to be smart, it should use CPUs for reducing the latency and it should use GPUs for maximizing the throughput. All right. So any questions about this design principles of CPUs and GPUs? Okay. All right, so let's see where the GPUs are originally coming from. So as you're probably aware of, the GPU stands for the graphic processing unit. So as the name suggests, it was originally developed and built for rendering graphics and rendering pixels on the screen. And what is the main application of GPU? Can anyone tell me? Like it was before, at least. It is now, by the way, but what was the main purpose that the GPUs were built for? What was the main application?
Like to make the graphics more appealing.
Yes, but what was the major kind of customers for the GPU?
Gamers.
The gamers, yes. So the GPUs were originally developed for gaming, and they had the biggest customer set in the gaming sector, and they were quite efficient for graphics rendering and games because when it comes to rendering something onto the screen, you just want to compute the values of the pixels and just show them on the screen, right? So this is a massive parallel work because the pixels are independent of each other. So you want to compute the pixel like as many as pixel values as possible. So that's why they designed GPUs that way. All right. So GPUs were designed for gaming and computer rendering, and they had like APIs like OpenGL, Direct3D, and nowadays they're also using another graphics API called the Vulkan. And these APIs are used for only rendering something on the screen. So if you want to draw a line, draw a circle, if you want to provide textures, compute shaders and things like that. So before 2007, you really didn't have a official way to use GPUs for general purpose computing. Like if you wanted to, I don't know, if you wanted to have some physics simulations or things like that, the GPU API didn't provide that functionality for it. So what people did was kind of a hack. So if you could frame, back in 2007, if you could frame your physics simulation or scientific computing application into graphics rendering, although they have nothing to do with graphic rendering, so then you could use GPUs, right? So back into 2007, people started to use this hack to use GPUs for general purpose computing, framing the problem as a graphics problem, but not really rendering something, but just using the power of GPUs for doing something, for doing some computations. And after a while, it became quite popular, and it was called GPGPU, or general purpose GPU programming. And then when NVIDIA found it, and then when NVIDIA found about it, so they said, okay, so now that people are really, really interested in using GPUs for high performance computing, why not providing an official way to do so? And that official way led to something called CUDA. So CUDA is a programming interface and parallel computing platform that NVIDIA developed both in software and hardware. So they needed to change hardware also to support CUDA that allows programmers to write high performance computing code on the GPUs. But still they support OpenGL and Vulkan and like Direct3D for graphics rendering. So nowadays, if you want to use it like NVIDIA GPU, you can have access to OpenGL for graphics rendering, and you can have access to CUDA for high performance computing. Okay, so that's when CUDA was developed and introduced. So in 2007. All right.
Sorry,
So
I have a question.
yep.
Can I ask? Okay.
Yes.
You said that GPUs were initially designed for gamers,
Mm-hmm.
and and you said that GPUs are throughput oriented. Yeah,
Yes.
but earlier you said that an example of latency-based
Yes, that's true.
design
I see
is
the
gaming.
contradiction. Yes. Okay. So
So,
the latency when it comes to
mhm,
games, the latency itself that you want to have the game faster, right? So you don't want to have the latency. Okay. So I think that that's clear. But when it comes to GPUs for rendering and rendering, so I mean gaming is not rendering itself, right? So gaming is rendering plus other things. So, but GPUs are like the GPUs maximize throughput when it comes to rendering something on the screen. So you want to render as much as pixel on the screen. So this is about the GPU, the throughput, right? But you want to reduce also the latency of that. So for gaming, both GPUs and CPUs basically are being used, but GPUs are mainly used for rendering something on the screen. But in gaming, you have like sound processing, audio processing, like gameplay mechanism and things like that, that are for the latency part. I don't know if it answers your questions.
yeah, thanks.
Okay. All right. So here, like OpenGL and Direct3D, they also developed originally for rendering on the screen. But the game engines, they also use this OpenGL and Direct3D for rendering, and also other libraries for audio processing, for gameplay implementation, for a lot more things. Okay, so this is a picture from one of the Jensen Huang's presentation, the NVIDIA's co-founder, back in, I guess, 2015 or something. Yes, I think so. And it shows the trends of using CUDA. So for example, in 2028, if you look at the CUDA downloads, it's about 150,000. And then in 2015, the number has become became 3 million downloads. So and you can also see other trends. The CUDA applications before that, like in 2008, just 1 year after CUDA release was 27. And then like after 7 years, like about 319. And you can see similar trends when like how the industry changed when CUDA was introduced. For example, if you look at the academic papers, you see that in 2008, like it was around 4,000 papers, like focusing on CUDA and GPU programming. And after a couple of years, it increased to 60,000, right? So it shows how popular CUDA is, and this shows the results up in 2015, and the numbers are still increasing. All right, and this shows the number of like developers, CUDA developers, like and it compares between 2018 and 2019. So in 2018, it's basically like you had like 800,000 of developers, the CUDA developers, and then you have more than a million. And then the same thing happens like in CUDA downloads between 2018 and 2019. So just to show you how popular CUDA is and how and a lot of people are using that. But I didn't tell you why CUDA is so popular, why CUDA is being used so much nowadays. So can anyone tell me why CUDA is very popular nowadays? So what is the main application that drives like CUDA programming and also drives like advancements in GPU manufacturing? Any ideas?
AI and LLMs in particular.
So that's the main reason that CUDA has become that popular. That's because of AI and how GPUs are useful when it comes to training AI models. All right. So this also shows that nowadays, by the way, this information is a little bit obsolete. It's about 2020. This shows that nowadays, like most of the supercomputers in the world, most of the top supercomputers in the world are basically GPU based. So most of them have GPU clusters, like thousands of GPUs. So for example, according to these statistics, so the first supercomputer in the US and the second one, like worldwide, which is called Summit, it's the GPU supercomputer. Also the first one in Europe as well. And you can see others as well. So most of the most efficient supercomputers nowadays, they are GPU computer clusters. And something that is quite interesting is this thing. So back in 2020, the second energy efficient supercomputer called Green 500 was also a GPU machine. But if you are a gamer, you know that when you wanted to buy a new GPU, you probably needed to change the power because the GPU needs more power, right? So can anyone guess why GPUs, although they burn more power, they are more energy efficient? Any guess? What is the formula for the energy? How energy is related to power, if you know some basic physics? Energy equals to what? Power
Power times
times what?
work.
Times what?
Work or
No.
Time.
Times what? Sorry, please again.
Time.
Yes. So energy, when it comes to energy, energy is the power times by time, right? So what happens in the GPUs that the energy is reducing although you have more power? So the power goes up on the GPU. This is pretty much obvious. What goes down here?
time?
The time, right?
Yeah.
So because GPUs execute code faster, although they burn more power, but the execution time is decreased like dramatically compared to CPUs, and that's why they're more energy efficient. So for example, you can try this at home, like open YouTube on your phone and like put your phone, like do it when your phone has like, I don't know, 3% of like battery, right? So do that. Just watch some YouTube videos because the YouTube videos are rendered on the GPU and see how for how many minutes you can work with your phone until the battery is dead. And do the exact same thing doing a web browsing or something or doing something else like. And you can see that when it comes to GPU workloads, the battery usage is even less compared to when you have CPU workloads, like a browser, web browser or something, right? So you can try this at home and you can see that probably when it comes to rendering, you're using less energy. By the way, you should be careful. This is not power efficient. The GPUs are not power efficient. They are energy efficient. And energy is the main thing that we really care about because that's what we really pay for, right? Okay. In Finland also, some supercomputers are available. So the biggest one is, as far as I know, is called Lumi, which is under that CSC that we talked about. And I think Lumi, they only have, as far as I remember, AMD GPUs. They don't have NVIDIA GPUs, but I think it's the eighth fastest computer in the world. I'm not really sure about the number because it's changing all the time. So if you want to see about the fastest computers, you just need to like visit this page, top 500. They list the top 500 fastest like supercomputers in the world. By the way, we recently started to have one like kind of data center, but a small scale also in Vaasa. So the opening was like last week. So in Vaasa, we also have, I think it's a multi-node system with 2 GPU nodes, and it's a zero emission data center in this case. So it's kind of energy efficient. All right. So I think we can stop here. And we can continue on CUDA programming and introducing the CUDA programming model tomorrow.